about chromatic roots and Fibonacci numbers.
Okay, thank you very much. Hello and good afternoon, ladies and gentlemen. And thank you.
Oh, sorry. You have the, oh, you do have the thing on.
Okay.
Maybe it's not switched on.
No. This? No, it's oh.
Did you switch it on? No, sorry.
Okay.
Sorry.
The title of my presentation is Chromatic Root and Fibonacci Numbers. This work is joint with Prof. Peng in University Putra, Malaysia. First, we need some introduction. In section 2, we investigate chromatic roots and golden ratio, and in the section 3, we investigate chromatic root and Fibonacci constant, and finally, we ask some questions. Okay, a graph G, we know that it consists of vertices VG and edges EG. All graphs are undirected. We say that a graph is planar if it can be drawn in the plane with no edge crossing. And a K-coloring of graph G is a mapping F from VG to set 1, 2, and K, where for every UV in H set we have FU is not equal FV. Okay, probably the most famous result in graph theory is the four-chlor theorem that says every planar graph is a four-chloroidal. Okay, and we need the definition of near triangulation graphs. Okay, sorry. Is a plane graphs with at most one non-triangular face, and a near triangulation with 3 faces is a triangulation. Okay, and the number of distinct K coloring of G denoted by PG and K and called chromatic polynomial and denoted by PG and K. A root of this polynomial is called chromatic root, and we know that a zero-free interval for a chromatic polynomial is an interval that polynomial has no root in this interval. Okay. Birkhoff and Lewis in 1946 have shown that minus infinity and 0, 0 and 1, 1 and 2 and 5 and infinity are zero-free interval for all plane triangulation graphs. And Jackson in 1993 showed that 1 and 30 to our 27 is also a chromatic zero-free interval. And Thomason in 1997 showed that there are no more chromatic zero-free interval. Okay. We recall that a complex number is an algebraic number if it is a root of some monic polynomial with rational coefficient. Corresponding to any algebraic number zeta, there is a unique monic polynomial P with rational coefficient called minimal polynomial of zeta, with this property that P divides every polynomial with rational coefficient having zeta as a root. And we know that two algebraic numbers, zeta and zeta star, are called conjugate if they have the same minimal polynomial. Since the chromatic polynomial is a monic polynomial with integer coefficients, its roots are algebraic integer. This is a natural question that which algebraic integer can occur as a root of chromatic polynomial. Clearly, those lying in minus infinity and 0, 0, 1, and 1 and 32 or 27 are forbidden set. To prove that B5 Braha number 1 plus tau cannot be a chromatic root, Salas and Sokal extended this result to show that these generalized Braha numbers for cosine 2 kp over n for n 5, 7, 8, and 9, and n greater than or equal 11 with k co-prime to n are never chromatic roots. For 10, they showed that the weaker result that B10 and B star 10 are not chromatic root of any plan near triangulation. Okay. Now we discuss about Fibonacci numbers. We know that Fibonacci numbers are terms of the sequence with a quite simple recursive functions. F1 and F2 is 1 and Fn is Fn minus 1 plus Fn minus 2. And golden ratio is this limit. We use this theorem 1. Fn is 1 over square root of 5 tau n minus 1 minus tau power n. By theorem 1, we can have this corollary that says if n is even, then Fn over Fn minus 1 less than tau. And for odd n, we have Fn over Fn minus 1 greater than tau. And also we need the theorem 2, Cassini's formula. Fn minus 1, Fn plus 1 minus Fn power 2 is minus 1 power n. Okay. Here we prove that this theorem that says for every natural numbers, the modulus of Fn minus 1 minus tau minus 1 Fn is in this interval, 0 and 1 over Fn. And this is easy proof. Suppose n is even, then n minus 1 is odd. By corollary 1, we have this inequality. By reversing, we have this, and by multiplying this inequality by Fn, we have this inequality. And by Cassini's formula, we have this relation. Okay. Also, we need the theorem 4. Tau n is equal Fn tau plus Fn minus 1 for every n greater than or equal to. Okay, the theorem 5 is a consequence of Salas-Sokal proposition in 10. Consider a number of the form p plus q square root of r. P and q is rational, and r is an integer that is not a perfect square. And we have this condition, p minus the modulus q square root of r is less than 32 over 27. Then lambda is not the root of any chromatic polynomial. Very easy for proof. If this is a root, then its conjugate also is a root, but lambda or lambda star can lie in this interval. Okay, now we prove that for every natural n, all natural power of golden ratio cannot be a root of any chromatic polynomial. By theorem 4, we can write tau n as like p plus q square root of r, where p is Fn over 2 plus Fn minus 1 and q is Fn over 2. Here we have p minus modulus q square root of r is this number. And by theorem 3, we have seen that this number is less than or 1 over Fn minus 1. So we have the result. Okay, now we extend Fibonacci number to an Alikhani numbers. First, we bring up this definition. And it's the Fibonacci sequence has this definition. F1n, F2n is 1, and Fkn is sigma. Okay, we can define an Alikhani constant as like this. Limit Fkn over Fk minus 1n. This is easy to see that Pn is the real root of this polynomial. Xn minus 1 minus x minus 1. And also the limit of Tn is 2. Okay, theorem 6 is a nice theorem in the pure and applied algebra journal that says that this polynomial is an irreducible polynomial over Q. So it is a irreducible polynomial over Z. And we need this theorem 7 that says let G have a graph with n vertices and k connected components, then every chromatic polynomial of G is this form, such that an is 1 and we have this condition. And if G has at least one edge, then 1 is a root of this polynomial. Okay, now we prove that for every natural n to n Alikhani constant cannot be a root of any chromatic polynomial. We know that phi to n is the root of this polynomial, which is minimal polynomial for this root. Obviously, this polynomial is not a chromatic polynomial, so we suppose that there exists another chromatic polynomial px such that p phi to n is 0. So we have f to n must be divide px. F to n in 0 is negative and in 1 is positive. By intermediate value theorem, f to n x, and therefore px has a root in minus 1 and 0. And this is contradiction because this is 0 free interval. Okay, now we show that all natural power of phi to n cannot be a chromatic root. Suppose that phi to n power m is a chromatic root. That is, there exists a chromatic polynomial as like this, such that p, g, and phi to n power m is 0. Therefore, we have this relation. We can say phi to n is the root of this polynomial. Okay, f to n lambda must divide it because it's a minimal polynomial, must divide q lambda. Similarly, f to n in 0 is negative and in 1 is positive. So q lambda has a root, say alpha in minus 1 and 0. Therefore, alpha m is the root of this pg and lambda. But we know that alpha m can be this in this interval. And this interval is a 0 free interval. So we have a contradiction. Now we can ask this natural question: how about 2n plus 1 Alikhani constant? Okay, we think that 2n plus 1 Alikhani and all power of them cannot be a chromatic root. Yeah. I have thought about this 2n plus 1 Alikhani about some months, but I'm not able to solve it. Only we have a theorem about 2n plus 1 Alikhani. Okay, we need this theorem that says let this is a chromatic polynomial of order n. Then for every I between 1 and n minus 1, we have this inequality. Now we can have this theorem for every natural number n. Phi to n plus 1 cannot be a root of chromatic polynomial of graph G with at most for n plus 2 vertices. Okay, we know that 2n plus 1 Alikhani is a root of this polynomial. Now suppose there exists a chromatic polynomial px such that phi to n plus 1 is a root of p. So we have this equation where gx is this polynomial. We can have this relationship between coefficients of p and g for this number m minus 2n minus 1 less than or equal to n plus 1, or m less than or equal for n plus 2. By theorem 7, x minus 1 must divide px. But we know that x minus 1 cannot be divided f2n plus 1x. So x minus 1 must divide this polynomial. And by this equation, this relationship, we have this relation that says am minus 2 n minus 1 is 0. And by theorem 10, we have am 0, am minus 1, and am minus 2 n 0. Therefore, Px cannot be a chromatic root. Only for m less than or equal for n plus 2. So this is an open problem for 2n plus 1 energy.
Pardon me, what were you just proving?
Yes?
What were you just proving?
Why?
What was it you were proving?
What is the theorem?
Yeah.
Yes, this is. We want to prove that phi 2n plus 1 cannot be a root of a chromatic polynomial of graph G with at most 4n plus 2 vertices. Okay, here we investigate some questions and remarks. Jackson in 1993 showed that for any epsilon there exists a graph G such that PGA and lambda has a 0 in this interval. This theorem says what is on the right of this number, on the right of 32 over 27. But the problem has been considered for some families of graph. One of these graph is a triangulation graph. Okay, we recall the question which says that is it true for any epsilon there exists a planned triangulation G such that PG and lambda has a root in this interval, where B and is their Bragg numbers. Okay, Beraha proved that the B5 is an accumulation point of real chromatic roots of certain planned triangulation. And Jacobson extended this to show B7, 8, 9, and B10 are likewise accumulation points of real chromatic roots of planned triangulation. Finally, Royle has recently exhibited a family of plane triangulation with chromatic rules converging to 4. Of course, it is an open for a question which other numbers in the interval can be accumulation point of real chromatic roots of planar graphs. The following conjecture of Thomason is one possible answer that says the set of chromatic roots of the family of graph consists of 0 and 1 and then subset of this interval. Now we can introduce this number ANI, I plus Pm, where I can be 0, 1, and 2. And we can ask similar question to Bragg question that says, is it true for any epsilon there exists a planned triangulation graph such that PG and lambda has a root in this interval, and I minus epsilon and I plus epsilon. Okay, note that A22 is 2 plus tau, and the Braha and Kane and Reed proved that the answer to this question is positive. And this table compares AN2 with PM. Okay. And these are my references. Okay. And thank you for attention. Any question?
So there is a zero free interval for chromatic polynomials of plane triangulations, which goes up to 2.54. It goes up to the octahedron.
Goes to?
So the interval from 2 to 2.54 is zero free for chromatic polynomials of plane triangulation.
Yes.
And with 2.54 we have the
Okay.
we have the octahedron. But could it be true that that everything between 2.54 and 4, that the chromatic roots of plane triangulations are dense. This would be stronger than the Baraha conjecture.
Okay, yeah. Yes, that's correct. Yes.
I mean, if I understand rightly, I mean, you've been looking at the aspect of chromatic polynomials from the point of view of algebraic number theory. Have people begun to look at things like Galois groups or deeper constructs for the algebraic number fields that you get from these polynomials? I have no idea. It's a naive question. Yeah.
I don't know. For our question, I think with this construction of this analogy constant and Fibonacci and generalized Fibonacci sequence, maybe we can construct some families of graph such that we can prove that roots of planar graph are dense in 32 over 27 and 4.
I'm just making the point, there is a huge mathematical landscape which this kind of analysis opens up, I would guess.
Okay.
I have started doing some work on Galois groups and chromatic polynomials, but it's still very early on yet. I've identified some families, but
Good.
still in process.
Yeah, I think you're absolutely right. I mean, the way I presented these four theories, the integer roots, the real root.
One.
Right. So the first one, the integer roots, has been studied since time immemorial. The real roots have been studied quite a lot, as Bill told us, but there's still a huge number of open questions. The complex roots have been studied not very much, and we have one or two theorems, 3 or 4 theorems maybe. And this area is almost entirely virgin. I think almost every paper in the field is cited in your reference list.
Yeah.
So,
Well, I mean, the thing that strikes me is that, I mean, algebraic number theory is a kind of natural structure to bring to this, especially if I look at the top, you had the exponential generating functions, which are wonderful complex series, which are integer valued. It just rings, that just says algebraic number theory to me is a kind, there are subtle hidden things going on there, just intuition.
Can we thank Saeid?